The talk today is going to be easy, especially to those who have majored in computer science. It's just going to be introduction, more like intro to an intro. I think we're going to plan to have like a longer 6-hour boot camp kind of session to actually like go through exercises of time series with code and even the productionalizing and all this. So I did not major in computer science. I'm an industrial engineer, like you heard. And so I didn't get a formal education in machine learning, as in I didn't have a data science class in school or a machine learning class in school. But industrial engineer, you know, I had my fair share of mathematics, statistics, and of course, operations research, optimization, which is basically the engine behind machine learning. And then I got to learn about machine learning more in my PhD dissertation research. In fact, I started using neural networks before knowing how neural networks work. So using MATLAB Simulink, and there's a blog there for neural networks. And I used to use it for short-term forecast, and it was working great. I had no idea at the time how neural networks work, but then I studied later and I understood. Not to waste too much time in the introduction, so this is the agenda for today. So I'll go very quickly about what is time series and what are the different options for tackling time series problems. And then there's some sort of a break in the middle, because depending on how the time goes, I didn't want to try to shortcut one of the most important parts of this talk, which is anomalies and their challenges in the industry. And I learned something from being at the school and then interning at Disney and then coming here to eBay, is that the problems and the competitions and the problems in the university that we publish papers on are far from being applicable in industry. So we will discuss that. And then if we manage to finish, you know, and we still have more time, so I'll go back to the technical talk and give introduction about how we can further improve and create dashboards for the machine learning models. So the first talk is what makes data set a time series. So is it the timestamps? Not necessarily, it doesn't have to have timestamps, but actually it's the sequence. Time series data are data that are recorded at equal intervals and in sequence, and there's dependency between one data point and the one before it. Not necessarily always dependency, but that sequence has to be fed exactly the way it is into the model, and the order of prediction matters as well. They may have or they may not have patterns. We'll go over this and we'll discuss what the difference between just a normal time series and a seasonal time series. So our data sets, like promised, it's real industry data set, but it's not eBay data set. It's still e-commerce data set. This is advertising data set, and it's available online. It's from the Numenta Anomaly Benchmark. So there is a link. Another thing is I have all my slides and my notebooks that I'm going to be going over uploaded on GitHub. So I'll share this in the end. I didn't want to share it in the beginning because I don't want people to be, you know, like reading from the notebooks instead of following me. Yeah. So the first step is data preparation. So I showed the link to the Numenta data set. Python has very good tools for data sets, especially time series. Pandas is the most popular. If you go to a big data level, there's another library in Python called Dask, which is more like, you know, scaling up of pandas. But for this time series data set, we can use pandas, and pandas can read from databases, JSON files, tables, CSV. This data set are available in CSV, so you just read it just by giving a pd.read CSV and then link to the data. And then the next thing is we need to convert it to a time series. So Pandas has the data frames and the series. The series is ideal for tackling a time series, especially if it's univariate. For multivariate, we can keep it in data frames, but our selection of models will be different. So for it, we just, you know, typical time series is move the timestamp to the index, so the index becomes a timestamp. And make sure that they are resampled correctly, because like I said, time series should have discrete time steps. So this is where the resampling to an hour is important. And then this is just like a view of the data set. This is how the data looks like. So a very common problem, especially in industry, is that there's no data set that's clean. There will be a lot of missing data. So what to do about the missing data? Ideally, there are imputing techniques, whether you use the average to impute the data set or interpolate. The only problem here is, especially with time series problems where the sequence matters, this might not be a good idea, especially if we have short-term and long-term seasonalities. You don't want to just interpolate if you have something that is, supposed to be replaced with a data point that is from the week before and not the hour before. So if we have a large chunk of missing data, like you can see here in this plot around September, the best thing to do is actually use the data you have before that to train models and use the trained time series model to impute the data set. That would be the best practice in this case. If you just have like one sample point that's missing, maybe just imputing it with an average or padding is good enough. In this case, we're actually going to partition the data, and then we will use the time series models to impute the missing data set, which is the best practice. So the other thing is the partitioning. So it's very common in research or even in industry that people split their data set to like 80-20 or 80-5-15 or 70-30 partitions, one for training the model and the other for validating the model. A better practice is have 3 partitions, like 70-15-15. The first 70 is for training the model. The other one is for validating, and again, this is the difference between industry and academia. Even when you validate the model and then you put it in production, it turns out not being good because the data that you used to validate the model is still not resembling the future data that you haven't seen. So it's better to have 3 partitions, one for doing the cross-validation, and then the third one is to simulate the honestly out of sample data set that the model have never seen and the parameters were not optimized based on. First type is using statistical techniques. Statistical techniques have been very common, very reliable. Honestly, only until the last few years, people weren't even thinking of using machine learning for time series, because in all major competitions, machine learning techniques would fail to statistical techniques. Only recently, I think there was a Kaggle competition about 4 years ago, and there is an M competition, M4, that was in 2018, I think, and the results were finalized in 2019. So this is very recent, and they found that some of the best models were a combination of statistical models and machine learning, and that's why people now are more aggressively tackling machine learning for time series. Before it was just statistics all the time. There are so many statistical models. The one we're going to talk about, which is also very popular and it's very reliable for time series, is the autoregressive integrated moving average, or AREMA. The underlying theory is that time series can be explained if it's decomposed to a trend, a seasonal part, and the noise. The trend and the seasonal part become easy and they can be taken away, and then the noise is where you do the statistical analysis on. So this is basically just a linear model. Well, statisticians wouldn't like me calling it linear because the regressors here are not independent. But I mean, it's basically a linear comparison of parameters and the data. This decomposition can either be additive or multiplicative. If our variance is increasing over time, that would be an example of a multiplicative time series, where the seasonality is multiplied by the trend is multiplied by the noise instead of being added together. A stronger model than AREMA is SAREMA. The difference between AREMA and SAREMA is SAREMA can handle as well long-term seasonality in the data set. AREMA, you can handle seasonality, but If your seasonality is very long, that adds a lot of parameters. Like you saw before, it was a linear combination, so you may fall in the problem of overfitting, and then convergence would be harder. So SAREMA would be more robust when you have a short-term cycle and a long-term cycle. And there's a Python library called Stats Models, which has both the AREMA and SAREMA models as well as other time series models. And this is the one we're going to be using. So we are going to be fitting a statistical SAREMA model for the data set that I showed earlier. And this is basically the decomposition. The first thing that happens here is what parameters we would feed into the AREMA model. So we have autoregressive parameters, and then we have the integral, which is supposed to resemble the trend, and we have a moving average. So one way to do this is to use the autocorrelation and the partial autocorrelation plots. Someone has a question at the back?
Is SAREMA algorithmically the same as AREMA? It's just like a nicer
AREMA, no, there's difference. Basically, AREMA is, yes, the seasonality. So you have more parameters in AREMA, but it's hard to explain, but basically as if you have two AREMA models, one for the short term, another for the long term, and they're multiplied together. So that's the difference between, well, that's very naively the difference between AREMA and SAREMA, but they are not the same. And the optimization of parameters is also a little bit different. SAREMA uses a technique called BFGS, which stands for 4 names. I don't remember the names, but the way you get the parameters is different. But both of them use Kalman filtering. And
is it hardwired to the seasonality thing, annual, monthly, weekly, daily?
You define the seasonality, or you do a grid search for the seasonality. So it's hard-coded, yes.
So why do you have frequency equals 24? Should it not be 12?
This is hourly data set, and the frequency is 24. We noticed that we did the correlation, and I'll show the correlation plots, but you notice that the highest correlation you get at the 24 interval. So this is a seasonality, which is also kind of logical. This is, e-commerce data, advertising data, and like people sleep at night. People are more active during the middle of the day, so it's 24-hour seasonality. So subject matter experiences also helps with improving the modeling of that. So the autocorrelation plots and the partial autocorrelation plots. Autocorrelation is basically like what it says. It's correlating one data point with another data point at a certain lag, just simple correlation. And using statistical methods, you can see the blue region. That's the confidence interval. Basically, anything that's outside the blue region would be a significant correlation. Partial autocorrelation is similar, except partial autocorrelation at, let's say, lag 2 is computed by after taking the effect of the correlation of lag 1. So it's after you remove the effect of the previous lags, then you compute the correlation, and that becomes the partial autocorrelation. So there are some rules of thumb, and then Duke, there's this link here. Duke has a list of the rules of thumb that you can apply to estimate these parameters. And what we see here is if you see exactly at every 24 interval of each of 24 lags, we have this kind of like spike. And that's how we know that this is a 24-hour seasonality. And we can see, for example, in the autocorrelation that the first 3 lags have good correlations. But in the partial autocorrelation, once you take into account the first lag, the second lag, and the third lag don't have that strong of correlation. Usually what you do is you use the autocorrelation plot to estimate your moving average, the number of lags for moving average, and the partial autocorrelation plot, you use it for estimating the number of lags for the autoregressive component. So just judging, we're not going to do any grid search or any optimization. Judging, we can decide that we want to have 3 legs for the moving average, because we see that we have here 3 legs in the autocorrelation that were significant, and just have 1 for the autoregressive parameter. And we use also an integral of 1. This means basically the first order differencing. So it's as if you are looking at the rate of change in the data, and you are predicting the rate of change, and then you add that back to your data set, and that gets you the actual prediction. And then we can train the model. The good thing about statistical models is that they are easily interpretable. So we can look at the summary of the model. We can get some statistical tests on it. For example, we can analyze the p-value and see which components were more significant. As you see, all of them were significant, except the lag 1 moving average were insignificant. We can also see the log likelihood, the AIC and BIC, which are more of like measures of the quality of the models. The smaller they are, the better. So if we're comparing different models. And there are some things like the heteroscedasticity. That means that our errors actually are increasing over time, so that they weren't normally distributed, and so on. Next thing is we forecast. Again, it's just a simple model to get forecast, and also statistical methods have the confidence interval built into them, so we can also compute the confidence intervals. And we can then look at the quality of our forecast. So this was our data set. The forecast is in green. As you see, the heteroscedasticity is obvious, which means that either this is bad model, or we just needed to use different parameters, or we assumed Gaussian errors where they are non-Gaussian, or we should have used a different order of differencing. There are a lot of things that could have gone wrong, but this is basically the beauty of heteroscedastic.
So if your data happened to be like a mean reversion process, where everything is kind of returning, could an ARIMA model capture that or not? Do you understand what I'm saying? So a mean reversion process would mean there's something is causing it to kind of return to that general operating region.
Yeah.
And it looks like here, obviously the uncertainty gets more and more spread out, whereas I guess.
Yeah. So to repeat the question, basically, is there something that we could have done to capture that effect? So yes, there are things. And honestly here that we're going to see later as we go through this presentation is that we will improve this forecast.
Okay. And specifically, I was wondering if an ARIMA model is capable of representing that.
Yes. Again, it's about how you set your parameters. So using a different order of differencing might have improved that. Using different parameters might improve it. There are other things that you can do without using the ARIMA model on its own. Is that remember, ARIMA works on the noise. So maybe you should have done different way of pre-processing the data set to get a noise that are better represented with ARIMA models. But this is actually a very good question, because there's another problem, which is most time series forecasting models are for short term. Long-term forecasting requires a whole different approach. In reality, even when you do short-term forecasting, when you are trying to do long-term forecasting, forecasting is still for the short term, and then iteratively you are improving, refitting your model or adding another model on top of it, which also we're going to discuss that later. And then, like using the other model to predict your errors, something we can do to predict the variance in the error, so that we can have a more robust error and confidence intervals in our models. So the next thing are Bayesian models. So we have discussed the statistical models. Now Bayesian are, for me at least, I prefer Bayesian more because they seem more practical. And instead of getting point estimates and the parameters, use Bayesian models when you want to get distributions on the parameters. And this is in general something that everyone in the industry should do. We shouldn't care about just a point estimate. We want to experience with several scenarios. So if you want to get distributions versus point estimates, use Bayesian models. The other thing is that Bayesian models are capable of handling non-Gaussian errors. So you can assume any distribution of your data set, versus statistical models, most of them are just made for Gaussian errors, assumed Gaussian errors. Another thing is if we have data limitations, if we don't have enough history, which is very important and critical to time series modeling. Bayesian models, if you have shorter history, because you can incorporate your belief about your data set, so it's kind of better. If I said, for example, my data set come from a normal distribution, so it's already going to do some sampling techniques from a normal distribution to assume data. And then ARIMA models and statistical models used a method called the maximum likelihood estimation. Bayesian models are just basically using Bayes' theorem for estimating the parameters. So this is Bayes' theorem that you see here on the right side. And basically it says the probability of H, so if H is our parameter set, so the probability of parameter given E, so in this case E is our data set, so it's all about getting this probability distribution of our parameter set. And we can include our prior probability. So if we feel that our data come from a certain distribution, it starts from there. So we apply our knowledge in it. And then the other thing is the integral part, which is the denominator here. And that is the probability of the data itself. And Bayesian methods use Monte Carlo Markov chains to get that value. So in Python, there's a good library for time series called PyFlux. There are actually other libraries. There's one called PyMC3, or PyMC if you are using Python 2. And these libraries have a set of models that use Bayesian methods to fit the models. So we are going to use the same kind of parameters we selected in the past, but the only problem with PyFlux is that there are no ARIMA models, so we're actually going to have to just use AR up to 24 hours. And similarly, we can interpret the models. We can look at the parameters and see the significance. But the other thing with Bayesian inference is that we can get the distribution of the parameters, so we can do Bayesian inference on the parameters. As we can see here, the red, very long one, that's the 24th lag, which we know that this is significant because, yeah, this is, of course, a 24-hour seasonal data set. So that gives decision makers more options to experiment and, have different scenarios based on different parameters and then be able to make better decisions. Similarly, we can, forecast, and we can also get the confidence interval. The forecast, we can see for the short term, at least it was more stable, but then it ended up getting worse as we go on. And one reason for that is because, we don't have seasonal. We just assume that the autoregressive part goes back to 24-hour. But that also can be improved. So the next is using machine learning models. And the machine learning is, now we have to define our problem differently. Reason is machine learning, there's no machine learning library, at least that I'm aware of, that is specifically made for time series. They are all made for supervised learning. So we have to redefine the time series into supervised learning by creating a set of inputs and a set of outputs. So basically, you take the time series and we put it in a matrix form where, our set of lags are our columns and then the target in another column, and that's the that process is called just conversion to supervised learning. So in doing that, we also have to consider that some machine learning models, actually the core machine learning model like decision trees or k-means and support vector machines, these are all models that are made for interpolation, not extrapolation. So meaning that they fit a curve to a specific data set, and anything you're trying to get, it is getting from the curve that was fit based on that data set. So it doesn't understand the order of the data. In other words, if you would say, we're going to fit a decision tree in a data set that has seen a maximum of 100, and I had a trend. So if I gave it during production, during deployment, if I gave it something that is 102, it will still make it match the same result for something that was at 100. If it's 200, it will make it match the same result of something that was at 100, because they only interpolate, they don't extrapolate, they don't understand trends. So there are ways of doing this, which is basically like we did with ARIMA, is that instead of fitting a data with a trend, we have to remove the trend from the data and just give them stationary data. And the other thing is that most machine learning models, they don't really have the assumption of normal distribution. Neural networks, regression, these are also called machine learning models, but they do have that. But if you use decision tree, then you can work without having to worry about the distribution of your data set. In the example here, I'm going to show is just using decision trees. Decision trees are just like the name says. It's a decision tree. It looks for splits in the data that maximize the outcome. So for example, here I have a silly decision tree about, what they are going to do with their day. If they have work, if yes, then they stay in. If they don't, then they look at the next data set or next feature, and then so on until you have like each node is pure, meaning that you can no longer have splits. That can also be transformed to a regression. But like we see here in the chart on the right side, when you use decision trees for regression, you are not exactly fitting curves. You are more like fitting like lines, straight lines to each block based on the similarity and the difference between the data.
Comment?
Sure.
Cubist, the leaf of each tree in Cubist, it'll fit a regression.
I'm sorry, can you repeat that?
With the algorithm called Cubist by Crinlin.
Yeah.
Like the C4550 guy.
Yeah.
So in Cubist, then at each leaf, it'll fit a regression. So you can have
Yeah.
a more continuous split.
So there might be a solution. This is basically just the binary decision tree. So I'm not aware of that algorithm. Cubist, you said?
Cubist, yeah.
Cubist, yeah. So there might be an algorithm called Cubist that actually feeds a regression model for every. Oh, actually, that's actually what's happening here. But it really depends on your decision tree, because if you use that, you may end up having a very large decision tree, and that might be overfit.
Well, it's up to you to control the
Yes.
size of the number of
Parameters.
per leaf.
Yes.
Before you fit a regression within the leaf.
Yes, that is.
Minimum number of records per leaf.
That is true. So we will discuss that later in this conversation, which is how do we do hyperparameter training, because decision trees on their own are definitely going to be overfit. So we have to control, the number of splits, the number of nodes, and the decision tree size in general. There is a library also in Python. I think everyone is aware of it, scikit-learn. It contains a lot of machine learning models. One of them is for the regression trees. This is just a simple without defining any hyperparameters. If we were to just use one. First, this is the pre-processing, how we transfer the data to a supervised form, and then training from the scikit-learn. We have to remember, in reality, decision trees on their own are not good. So ensampling, like using random forest or gradient boosted trees, is a better option. And the other thing is that we do need to select the parameters carefully. So doing grid search or some other methods we will discuss later. So this is the forecast with the simple decision tree model that we created. And that was created with the friend set. The other thing is that now that these models don't understand that it's time series, and we had to transfer it to a supervised linear problem, then we have to see how we're going to forecast the long term. One way to do this is to do a rolling forecast, meaning that you forecast one time step ahead and then feed it back into the model and then forecast the next time step and so on. And that's what I'm doing here, rolling. But also these models can map a set of inputs to a set of outputs. So you can have a model that, let's say, forecasts 24 outputs of 24 time steps ahead in just one go, and then you feed these 24 back in, and so on. This was the output from the simple decision tree that we did without any hyperparameter optimization or anything. As you can see, probably the first couple of hours were good, and then things went bad after that. That's normal if we just use models without doing any tuning.
Is that rolling for? is that rolling forecast deterministic once you start going to the future?
The question is that rolling forecast deterministic? I think so. I mean, you are assuming assuming the input, that you know the input. So that basically you are increasing the error as you go. Yeah.
So here you just did one time step ahead regression of the last time step.
Yes.
On the previous one, and then you rolled it forward, right?
Yes, correct. So the question is, I predicted or I forecasted one time step ahead, and then I used the history before that time step ahead to regress it, and then I used that time step that I regressed as new history in addition to like also other history to regress the next one and so on. It will not be good. That is correct, and we will get to that. Yeah. So the other thing is, let's go to deep learning. Again, deep learning, I mean, some people like to say deep learning independently. It's still a machine learning technique. But it usually refers to neural network, a specific type of neural network, which you actually have several layers, and that's what makes it deep. Multi-layer perceptron is the most basic form of the neural network, the deep learning. When someone says artificial neural network or someone says deep learning, usually they are referring to a multi-layer perceptron. And then, of course, variations of these. Multi-layer perceptron is also the closest thing to a statistical method from machine learning. The reason is what's happening in every node or in every neuron is basically a linear combination of parameters and predictors, and they are fit with the same way a linear regression is fit using an algorithm called the gradient descent. But now, because we can stack these layers on top of each other, or stack these neurons on top of each other and like in sequence, so we can use a nonlinear modeling technique to capture what linear algorithm on its own cannot capture. The simple multi-layer perceptron is a feed-forward, and it has no memory. And I'll discuss in the next slide what I mean by no memory. So the next thing is another type of deep learning models, which is called the recurrent neural network, RNN. The difference between this and the normal neural network is, and instead of just mapping an input to an output, where in every iteration you are computing the output with an independent set of input, recurrent neural networks also consider the output of the last step during the last iteration in the current one. So as you see here by this kind of red cycle, so you have input, output, but you're also taking the output of the last iteration or the last time step. And that's what makes them recurrent, meaning that you are not just learning from your input data for this particular iteration, you're also learning from the result of your last iteration. And that happens across the batch. So if I'm feeding a batch of 1,000 data points, I'm basically in every data point, I'm learning from the output of the other data points. So that kind of gives the model what's called the memory versus just the MLP. Because it learns from the previous inputs, not just the current input. This system has been very good with natural language processing applications, but there are still problems here. One is called the vanishing gradient, the exploding gradient. Basically, these are problems because as I'm doing the gradient descent, and I'm multiplying the weights across different layers. If my weights are very, very small, then I'm multiplying almost zeros, then that my gradient will vanish. Or if they're very large, my gradient explodes. So there's another solution to this, which is another form of recurrent neural network called the LSTM, or the long short-term memory. This is better with the problem of vanishing gradients. The difference between this and RNN is instead of just learning from the history, this has a system, which is how this neuron is formulated, that decides what to keep in memory and what not to keep in memory. And that's why it's called long short-term memory. It has something called the forget gates. So basically, this is capable of holding information from even thousands of steps in the past if it finds that these are actually important and they improve the accuracy. And at the same time, it removes information that may be problematic or might not be relevant. And this is called the state. The state of the unit is what it keeps carrying over the different iterations from information. So it's basically having something happening like another memory on the side that keeps information or forgets information as needed. So in Python, there's a library called Keras. There are other libraries, there's PyTorch as well, but Keras is the one I use. Before, we also need to pre-process this as a it's called the supervised learning form. The one difference here is that when we formulate the inputs, we were just formulating a matrix of observations and features. In recurrent neural networks, you need to give it a third dimension. So it's basically observations. You have to define how many time steps and the feature for every time step. Then we decide the architecture. So Keras, when you are building a neural network on Keras, you first have to call the first thing, which is called sequential, meaning that you're going to be adding layers in sequence. That's just basically how we started from Keras. And then you can add the layers, and you can define the type of the layer. And you can actually play with this. So you can have some MLP layers on top of some LSTM layers on top of some RNN layers. You can play with the architecture. People are playing with the architectures all the time. And then, if something works, they end up publishing that and making that open source, like WaveNet and things like that. It's just a specific architecture. That's what it is. So here I'm just doing a simple architecture, but it's still a deep learning because there are several layers. I'm giving 2 layers of LSTM and then 1 layer dense. That's the output. 1 layer, but it also has 1 node, meaning that I'm only doing 1 step forecast. I can do multi-step forecasts if I want. If I feed it instead of 1 feature for the output, I can feed multi-column output, and then that becomes a multi-step ahead if I want.
Does the 5 on the first line mean that you're looking at the previous 5 time steps at every time? Okay.
Yes. So again, that's my shape. So I have the observations, which is basically my batch size. And then for each observation, how many time steps, and for each time step, how many feature. So I have 5 time steps I'm looking at, and I have 1 feature for every time step. The difference between using neural networks and other statistical machine learning techniques is that actually there's no easy way to determine when a neural network must stop. So you basically just select a number of iterations and hope that that's a good number of iterations.
So kind of to expand on that point, is basically a neural network chaotic? That is, in essence, if there is no, beforehand you'd go on and see basically perhaps the weights potentially start going to 0, or they go on and amplify up, or they hit a steady state. That's not true here? I mean, it turns out that basically these things could oscillate and blow up?
So you can have a rule, you can define a rule, but again, I repeat the question. So is our neural networks chaotic, meaning that even if, the change in your gradient or your tolerance is low, they will keep going, they won't stop? And the question is, and the answer is yes and no. There are some options in the library that you can use to, kill it, make it stop, based on, how your tolerance is improving, or how your error is behaving next to your tolerance. But what I meant before is when we use, for example, AREMA uses statistical techniques to decide when it is going to stop, like the AIC and BIC, and also depends on the number of parameters in it. In neural networks, that is not the case. The complexity of the model can keep increasing, and like if you have a deep learning model that uses, a very complex architecture, another one that uses a very basic architecture with smaller set of columns, the network itself has no way of deciding, oh, this is a very complex, or this is overfitting. It has no way of learning that this is overfitting.
In an earlier slide, you divided your time series into a validation set and a test set.
Yes.
Can't the validation set be used for that here?
Question is, can the validation set be used? And yes, the validation set can be used. Actually, Keras allows you to add a validation set while it's fitting. I'm not doing this because I'm just doing like simple stuff. But yes, you can use your validation set, and you can put a rule, a stopping rule on your validation set. Problem is, validation set does not always help when you start looking in the future outside of the validation set, because you would basically be fitting a network to a specific set of data, and it will fit it very well to that specific set of data, and you will see that, and then you put it in production, and it's nothing like it told you during the validation set. So these are very good questions, by the way. So the next, I'm just going to forecast. Again, this is rolling forecast. So meaning I'm forecasting one step ahead and feeding it back into the model as a new input and so on. And then when we look at that, we can see that, one problem is that I just used 10 iterations. That was my judgment, but 10 iterations maybe weren't enough to capture it. But again, this is also a problem of rolling forecasts. The error increases over time. So to speak a little bit about this, there are different ways of doing this so that we like better than the rolling forecast. The first one is the iterative forecasting, which is what we did. That's called the rolling forecast. The other thing which we also can use as rolling forecast, but is to use direct forecasting, meaning that sequence to sequence, meaning that instead of forecasting 1 point ahead of time, you can forecast 24 ahead of time. So I can, for example, map the last 24 hours to the next 24 hours, and then use that to forecast the following 24 hours, and so on. And then the third thing, which is actually my preferred for seasonal time series data, is if you can decompose the time series, since machine learning models don't really understand the inherited sequence in the data. So if you can decompose it like by the day of the week or the week of the year, and then have a neural network for each particular day or week, and that can help with the problem of the error increasing over time. Okay, so this is the pose. This is the part I wanted to talk about, the nature of anomalies, before getting back to like the Python stuff. So these charts are taken from Anodot online documents. Anodot is a anomaly detection as a service company, and they are speaking about the common types of anomalies you see in industry. One is the global anomaly, which is, like you see here, is just basically a data point that's way outside the distribution of your history on its entire history. The other thing is the conditional, which is a data point that's not outside the distribution of the data, but it fell in a specific part or a specific group where it's outside the distribution for that group. So that's, for example, if you have seasonality, then your distribution is going to be large, but depending on the hour, that distribution is going to be smaller, and then you can have a data point that is farther away from the mean for that particular hour, even though it's not farther away from the mean for the entire data set. And then the other thing is combined or collective. Collective anomalies are basically anomalies that in a single metric, they are not really away from the mean, or they are not out of the confidence intervals, but if you sum it over several metrics, it becomes away. So if I have like a small deviation, that's not sharp deviation in one metric, that might be okay. But if at the same time I had the same deviation in 10 other metrics, then there might be something going on there. And then there's something that I want to add, because that's my work here. So a type 4 of anomaly, and that's what we call a slope lead anomaly. So everything we have talked about before is, like this chart we see on the left side. What we face, and that's what we try to solve here at eBay in my team, are anomalies that regardless of if you do a combined metrics or if you do the global, it's still within limits. And when you detect it, it's already too late. And that's the difference between an outlier and an anomaly that's not an outlier. Basically, every time you hear anomaly, people are referring to outliers. But in reality, anomalies are just things that are not supposed to happen, even if they are not outliers. So for example, here in this chart I have on the right side here, there are 3 indications of a problem. And the outlier only happened the last one. The first indication is that I have a downward trend that I shouldn't have had. And that downward trend, when I'm doing rolling forecasting, or even if I'm doing forecasting, not rolling with actual data points, but I'm just retraining models and feeding it, it's biasing the forecast. So the confidence intervals will also have downward trend. And then, and at that second arrow, my rolling variance started vanishing. Meaning that, I used to have this kind of like zigzag noise, and then all of a sudden my noise became lower. And then after that, that's when I had a sharp enough deviation to be labeled as an anomaly. But that's already too late. So in reality, in industry, we don't really care about outlier detection, because outlier detection means we already are too late in discovering the problem. So the question is, can we do things to find anomalies, before they become outliers? And that's the work that my colleagues and I do. I'm not discussing this today, but hopefully we'll get an SRE-Con next year, and maybe KDD, because we have stuff that we file patents for. But different ways, non-parametric techniques, and techniques from simulation and optimization theory to answer this. Another thing, just to kind of wrap this up. So in industry, we don't care about outlier detection. We care about problem detection. The confidence interval approach has a lot of problems. And there are high false positives with anomaly detection. When we use confidence intervals, the approach of confidence intervals, that becomes non-actionable. We cannot take an action on that because it's already too late. Sometimes the anomaly happens, and the outlier happens, and then no more outliers, because some automated system kicks in, to fix itself. But the loss has already incurred. So we want to stop things before, the automated system goes to roll back to the last working code or something like that. And again, it's contaminated because, if I have outliers that are not detected, they end up contaminating my future predictions and my confidence intervals on my future predictions. So it makes it even harder to detect it in a prompt time. So far we have been talking about parametric approaches, except decision trees. Decision trees are not parametric approaches. So using non-parametric approaches might be one of the solutions, like this animation we see here on the right side, which is basically taking a rolling time window and doing clustering. So basically you are comparing a group or a time window of data to what you saw before. And that might be one way to capture, these slow deviations. Might be that's not actually what we're using, but that's something I used in my dissertation, and that was working. And another thing is, even though this is one way of capturing anomalies that are taking a while to develop, there's still a value in capturing it at the same time it developed, other than waiting for my time window length, which is, let's say if my time window is 12 hours, the clustering technique might find it after 6 hours of anomaly if I collected enough data for 6 hours, but that's, again, 6 hours wasted. So going back to the talk, I mentioned the hyperparameter optimization in several locations, and that's basically how we improve these models by selecting the right set of parameters, whether you're using time series models or we're using machine learning models. There are 2 ways that are excessively used. One is the grid search and the random search. Grid search is basically for every parameter you define a set or a list of options for that parameter, and then grid searches, you combine all the combinations and fit a model for each combination, and then score it, find the best one. That obviously can take a lot of time and a lot of computing resources. So another solution that might be better is using random search. Random search is basically you're randomly sampling from all these combinations, and hopefully you will get the good one through random iteration. And then there are other options that are not, in the most popular machine learning models, libraries, but there are evolutionary methods and there are Bayesian methods. These kind of start like random search, but it's more like guided random. So based on, the number of iteration you are at, it has some information from before, and you can use that to guide the direction in which a parameter should change. If anyone works towards Markov chains, this is an application of that. Or using evolutionary programming like, genetic algorithms. Genetic algorithm usually, instead of just computing a completely new random iteration, it uses the most winning iterations from a previous generation, and then just changes one or two things in that and then moves it forward. So it's a little bit more guided than just doing random search. So hyperparameter optimization, scikit-learn has a library or has a code for random search, a code for grid search. And both of them use multiprocessing with another library called JobLab. It uses the multiprocessing module in Python. So if you have a lot of cores, you can actually achieve more speed, because then you will split the models on these cores. Another way, if you're using a Spark cluster or something like this, then that's a lot better. If you're using these libraries, then the models should have the required methods, the fit, the predict, and the score. It depends on models that have these methods in them. So if the models don't have this method of them, you can wrap the model in another module that you define or another function that you define, and then you add these methods to them, and then use the grid search. Or you can define your own custom grid search, which is what I'm going to do, because there is no good grid search made for stats models. Stats models have something that's supposed to resemble AutoArima, but it doesn't work. So we are going to define our own custom grid search. We have to first think when defining our own custom grid search is to define the accuracy metric. MAPE, it's not the best metric. It's actually very bad, but it's very simple. A better metric would be what's called MACE, or mean absolute scaled error. But just, because this is intro, MAPE is simple enough for us. And then we define, a test function, which is basically computing the error on the model, and then we have to define that as a separate function. And then define a function for wrapping the parameters, how we're going to feed the parameters into this grid search. Because ARIMA takes the inputs different than other models, so you have to give that input to it. And then this is basically the grid search, and I'm using here JobLab. I just haven't, so I'm basically doing the same thing that grid search is doing in scikit-learn, which is using the multiprocessing module to spread out the different combinations on different processors. And then I do the training, and I just took a screenshot of my processor here to see that I had a 24 core on my machine, so all 24 core became busy because each one of them is now taking a model and fitting it. And then I'm collecting all the outputs of these models to compare them. These were the top 5 models. So we can see the accuracy that's based on the MAPE. So the best one was based on an autoregression of 1, no differencing, but there is seasonal differencing of 1 and a seasonal moving average lag of 3. Someone has a question?
Yeah, question. So this looks a lot like the way I do, like stuff I do.
Yes.
Is this, in terms of the way these things are done, is this basically a grid search? Is this looking at the, an NQ, basically all possible parameters going inside this thing, or maybe you've said this already, I just missed it, or is there in fact some kind of a search algorithm that's working in the background in figuring out what these things look like a genetic algorithm or anything.
Yeah. So the question is this grid search that I just performed here, is it based on all possible combination of parameters, or did I use a more like guided way, or Bayesian or genetic algorithm to like help search for the parameters? And the answer is it's actually, I'll go back, it's actually based on this set of parameters that I provided. So I still used my judgment. So you can see here P, which stands for the autoregressive, I tell it to use any range from 0 to 4. So I gave it a range for each parameter, and it tried every possible combination in this range. You're welcome. But again, this is because I'm just doing simple intro stuff here. So in a better, in a longer session, we can tackle how we can actually do more guided random search than just try every possible combination, which is just a lot of compute for no reason. This was this case. So we found the best combination here. And the other thing is, let me see, did I miss it? Yeah, so I wanted to note here, and that if you see highlighted in yellow, is that this combination of parameters that I gave it ended up being 1,024 models, just by like doing 4 options for moving average and 4 options for autoregressive and 2 options for the differencing. When you get the combinations, all possible combinations, this increases up very easily. It becomes 1,000 something, and because I'm using the multiprocessing technique, it only took me 17 minutes. Like that's only a few seconds per model. So that's the advantage of multiprocessing.
MSE as the metric. What is the percentage error, like of the forecast value? MSE divided by the.
So MSE is the mean squared error. Are you reading percentage here somewhere? I'm not
I was asking, roughly speaking, normally we test the accuracy as like a percentage, right? So you could actually divide the kind of error in absolute units divided by the average value which you expect.
Yes.
Is it 3%?
Yes. I'm sorry, I repeat the question. Yes, the question is, I'm using MSE, so where is the percentage error? And that's because I did mention before that I'm using the MAPE, the mean absolute percentage error. I might have done a mistake here. I think that's actually the mean absolute percentage error. That's not the MSE. So I don't see where we see MSE here, but that result here, that accuracy is based on the mean absolute percentage error. So if I go back here, you see here I defined a MAPE function, define MAPE, that's the mean absolute percentage error. And then when I called my GS here, you see the line which says GS equal grid search, and then I have a parameter there called the error function, and then I gave it the MAPE. So I'm actually using the mean absolute percentage error. Let me see if I can point with this. What's this point? Yeah. I cannot point with this, but it's right in the line that starts with GS. You see here that I'm defining that I'm actually using the mean absolute percentage error for computing the accuracy. So that's the mean absolute percentage error. 13%, that doesn't give you the output. So that here would be 13% because yes, in my error function, I'm not multiplying by 100. So I didn't multiply by 100, so that's basically 13%. 0.13 is basically 13%. So let's put this into like, let's create the forecast now with the optimized model. So here I did the grid search with the validation set, and then I left the test set, and we can see here that now we don't have the same problem of the heteroscedasticity with the confidence interval or with the error. So now I have a more reliable forecast. We can see that the error improved by far. And that's more useful. So the last thing I'll talk about is the unsampling. So far we have talked about the basic, very basic models, how we tune them, and then the other thing we can do is just we can ensemble these models so we can improve our accuracy by actually combining different models together. One sort of ensampling is what's called bagging. Bagging is basically having several models, weak learners, kind of like blind models. Each one of them is looking at a specific part of the data set and making their own prediction. That prediction is probably going to be bad, but when we combine them all, aggregate them by some method, we will get a better prediction. Boosting is adding the models, but instead of having them work in parallel, they're working in series. So we have a model or a set of models. We get the forecast of them. We compute the error, and then we'll put another model on top of that, to improve the error, and then another model on top of that, and so on. So that becomes a series. And then stacking, which is basically a combination of both. We can do this manually, or we can use, for machine learning, there are some libraries for bagging or for boosting or stacking decision trees. So for bagging decision trees, there's random forest that basically fits decision trees in parallel, but each one of them is only looking at a subset of the data set or subset of the feature set, and they're very weak, and they're much smaller, and usually this makes them generalize faster instead of like overfitting. So basically, this is how we forecast with this. So one thing I wanted to mention is this is all posted on GitHub, so you will be able to see all this code.
Question?
Sure.
On the meetup site for the event, can you post a link to the GitHub and to the PowerPoint?
Sure. Yeah. So I'll post this also on the meetup site. These are, by the way, things that I just created over a couple of weekends. So they are very, very basic. A lot of that can be done in this. So this is the output of the random forest compared to the decision tree. We still see that it's bad with the selection I gave it, but at least we can see that it did capture seasonality. So if you remember the other decision tree, which is in the bottom here, it didn't capture seasonality at all, but this one captures seasonality. And as you can see, it's more general, as in the predictions didn't have so much variance in them. They were more smoothed. The last thing is to conclude this. So we briefly discussed different methods. How do they actually compare with each other? So this is taken from a recent publication. This is from the Makridakis. I don't even know if I spelled that correctly. This is what's called the M competitions. There are 4 of this type of competitions. This is different than Kaggle. These competitions actually happen like once every decade or so. They are not every year. And these are the biggest when it comes to like time series. Reason is, compared to Kaggle, this is not about using one clean data set and trying, to like stack and bag the best combination of models to, fit to the data. This is, every data scientist have to come with their own technique, or with a technique even if it's not their own, but it has to perform well across hundreds of thousands of data sets, not just one data set. So again, when we talk about industry, versus academic versus publication, someone had a question in the back.
The scale is less or more? Is the left values?
Yes. Yes, I'm sorry. So on the chart, the y-axis here, that's the mean absolute scaled error, MACE. I kind of wrote this above it, meaning that the smaller the value, the better. Yes. Excuse me, what is the question?
What is some
So yeah, there's an ARIMA model here. That's the second one.
some RIMA? I did not see it.
Yeah, so ARIMA is just another variation of ARIMA. So basically, that's actually, it's not even just an ARIMA model. That's an automated ARIMA, and that does include seasonal features in it. But yeah, these labels, I mean, there's a link to the paper, so you can see exactly what every model is. But the first about 7 set of models, these are all basically statistical models, are like different types of exponential smoothing or other state space models like ARIMA. And as you see, they were the one that performed the best here compared to machine learning models, and compared to other approaches. Now, this was taken from the M3 competition results, and the authors added some more methods on that data set to also like test them here, because the first like that M3 competition didn't have neural networks, so the authors added neural networks to it, and you can see them here in this chart. But this was, I believe, from 2018, and as I said, the M4 competition, the results just got published in 2019, earlier this year. So this paper was before publishing the M4 results. And the M4 results, one of the top methods, did have a combination of deep learning and statistical versus just using a statistical. So far, statistical methods are the more reliable, the most reliable when applied to a large set of data sets.
Is this more a reflection of simpler things are easier to automate, and the more
Yes.
complex things, you know, if you handcraft this, I bet I could beat an ARIMA.
Yes. That's a very good question, yes. Is this more about, simpler methods are better in general than, more complex models?
No, easier to automate, not better.
Easier to automate as well, yes.
For a large data set.
More simple methods are both easier to automate, are better, and also better accuracy. So in this publication, they actually, the authors compared the models not just based on the accuracy. So if you go to that link or to that paper, they actually compared the models on complexity. And you will see that there's a linear relationship, or there's a correlation between complexity and accuracy, meaning that the more complex models tend to be worse than the more simple models.
Can you describe briefly the problem which this is attacking?
Yes. So that's again, the question is, can I describe the problem which this was attacking? So this is the M3 competition, and one of the advantages of this over Kaggle is that this is not one problem. This is the results across 3,024 problems. The M4 was over 100,000 problem. So this is not just one data set. There are thousands of data sets, and this is like, the average across them. So again, Craig's point was very good, which is, if you give me one problem, I can handcraft, a complex model that fits that problem perfectly. Overfit.
No,
That's
that can generalize well. I've competed a lot of times.
for generalized for all other data sets, or just for a particular data set, and then generalize for the future of it.
For a particular data set.
Yes, that is also
I
true.
can generalize well.
Yes, you can, if you have one clearly defined problem with one type of data set, you can basically create a very general, very robust neural network for it that works very well with it. I'm not going to say that that's the easy or the best way to do it, but you can do that. Question is, can you apply it to a different data set? And that is less likely with more complex methods than with just basic statistical and Bayesian methods. So the last thing, just is only going to take a couple of minutes, is part of the job of a data scientist is not just create the results, but also how you communicate the results. Python has a very good set of libraries for communicating the results. Some of them are even like production ready, as in like they work with HTML code, or you can publish them on the web. There is a tool called, there is a library, actually a link called pyviz.org, which helps you, based on your needs, select which Python library to use. My favorite Python library is Bokeh, which enables you to create dashboards and publish them. And so you can put this in a production server, and then you get the link, and anyone can access this dashboard, and it's interactive. I created in that code a very simple, very simple dashboard. So I can show it to you here. Let me see, I need to log in. Parent's been on standby for a while. But all right, we're here. So basically, I took the first the top 4 ARIMA models from the grid search, and I put them on a dashboard when I put like a simple controller that lets you switch between them. The good thing about Pokey is that it's built for data scientists, as it believes that data scientists don't need to like know a lot about UX and JavaScript and like the other languages that UX people use. So this is all you can just build this dashboard just from Python command line. And you can make it interactive. Here I just added simple stuff like I can hide and show parts of it, and then a controller where I can switch between them. So I also include the code for doing that. And as you can see, this is now served as like an HTML. Yes, this you can also stream data to it. Pokey supports that. Question is whether I can change the data. Yes, and actually, I mean, of course, because I have this is being recorded. I actually have dashboards that I create for my team with this, and they're production ready and everything. And they interact with Flask, which is another Python tool, which you can actually in Flask also like add some parameters that you want to change, like try different simulations, and then you get a dashboard specific to parameters you give it. And of course, as the data changes in the database, this can read from the database, so it always fetches new data and so on. It's a very good tool. And going back, and actually this is it. So if you have questions, I'll be taking questions now. The slides are shared on this link, which I'm going to share on the meetup page, and that's my email also for questions, feedback. There's a question there. The question is in my data set, am I using UTC? UTC time format, or am I not using UTC? And if I'm not using UTC, how do I account, for the different locations where my data is coming from? Because different locations have different time zones. And before I give you the answer to that, this is actually a very good question. The reason is, people who create the database, I don't think they put in mind that there are data scientists that are going to be using their data for time series in the future. So they are created with time zones specific to the location of that database, or some of them are actually good enough to create them with UTC, like to record the data with UTC. So this is actually a big problem. The thing we do here is that we do try to convert everything to UTC. So if we have data coming from different places, and we are lucky enough to know, where's this data coming from. So in Python, there's a tool, PyTZ, where we can manipulate any time series, any timestamp to make it general in UTC. Or it's even better if you are using machine learning. And in machine learning, you don't need to really put the timestamp itself or something like this. So just use the epoch. Epoch would be the best thing, which is also based on UTC. There's an option if my training set, is in different time zones, I can normalize it, normalize the time zone, or normalize it across the time zones. That's an option, yeah. So there is a Kaggle competition right now for time series. Here's my question to that. Did the competition start yet, or didn't start?
It started 2 weeks ago, and it's open for the next 6 weeks.
So how many data sets in the competition?
One.
Just one. That's Kaggle. So it's always fun to tackle Kaggle competitions. Problem is, it's just one data set. How do we know that it will be well? And people publish based on problems similar to data set, or they choose a couple of data sets from public databases like the Numenta, which by the way, are also not very representative of the industry. Thing is, from my own experience, can spend a lot of time on that. Maybe you can even win it, beat it. But still, that's not going to be something that the industry can use. Industry wants something that works over 100,000 data sets and not just optimized for one data set. The question is, we are not really controlling for non-stationarity. Even when we showed how we tackled the trend, we just used first order differencing, whether in machine learning or the statistical methods. That is true. I have not shown anything that's related to how to tackle stationarity at a more advanced way. This has been very simple. Just to give you a few comments on that, there are a lot of arguments on, for example, deep learning models, is whether we need to control for stationarity or not. Some argue that because you are using a complex way of transferring a linear problem to a nonlinear problem, then you don't really need to control for it. Let it learn the stationarity of the data set. I don't always agree with that, but apparently it works. The Amazon people said let it learn the trend and the changes in the trend. We did use first order differencing. That might be something that we also want to optimize in grid search, which is what kind of differencing we want to use. Again, what we are using here at eBay is actually not based on anything forecasting, so we actually don't even care about stationarity. We are not presenting this here, but we're using non-parametric approaches that do not forecast in the future, but they actually forecast the current, using the current and not using the past. We're not going to get into that, but that's another way to tackle problems if your goal is to do anomaly detection and your data have multiple or like non-stationary in a more complex way.
Thank you for your...
Thanks.